everyone, in this video we're considering this problem 3161. Before you watch this video, please attempt to solve the problem yourself, and if you're stuck and then really stuck for at least 30 minutes, then look at the solution. But then anyways, please look at the solutions when you finish solving the problem. Okay, so let's read it together. The space shuttle launches an 800 kilogram satellite by ejecting it from the cargo bay as shown. Okay, so we have our space shuttle, and we have a satellite. Okay, so the space shuttle launches an 800 kilogram satellite by ejecting it from the cargo bay as shown. The ejection mechanism is activated and is in contact with the satellite for 4 seconds to give it a velocity of 0.3 meters per second in the z direction relative to the shuttle. Okay, so the shuttle ejects the satellite, and then the velocity of the satellite relative to the shuttle is 0.3 meters per second in the z direction, where the basis is given like this: ex, ey, and ez. Okay, the mass of the shuttle is given, which is 90 megagrams. Determine the component of the velocity Vf of the shuttle in the minus z direction resulting from the ejection. Also find the time average of the ejection force. Okay, so here we have two bodies. Let me name them maybe body A and body B so that I don't have to keep writing space shuttle and satellite. Okay, so again we were given that the velocity of the satellite minus the velocity of the shuttle, I'm gonna call prime because that's post-ejection, is equal, or along the vertical, dot ez is equal to 0.3 meters per second. So the prime denotes post-ejection quantities. Okay, very well. So this is what we're given so far. So then, before the satellite was ejected from the space shuttle, pre-ejection, the two bodies were moving at the same velocity. So VB would be equal to VA pre-ejection. So in particular, VB minus VA dot EZ is equal to 0. So these are the pre-ejection velocities. Okay, so let us see. We have 4 unknowns so far. 4 unknowns. VB dot EZ, the vertical component of VB, VA dot EZ, and these two are related, so we have one equation here that relates the two, and then VB prime dot EZ and VA prime dot EZ, the vertical components of the post-ejection velocities. We have 4 unknowns, and so far we have 1 and then 2 scalar equations, so just 2 equations. Okay, so then we need more equations to be able to find the velocity component Vf of the shuttle in the minus z direction resulting from the ejection. So basically what they want here from this sentence is VA prime dot EZ, sorry, that's what they want. That's the first part of the question. We'll deal with the ejection force later. Speaking of forces, let's draw the free body diagram of the space shuttle and the satellite. Maybe each one on its own. This is my space shuttle. Again, not the best drawing, but let's make it work. Okay, so this is in space, really no gravity. is up there, so no weight is acting on the space shuttle or the satellite. However, there is the force from the satellite on the shuttle and the force from the shuttle on the satellite. So I'm gonna call this force F and the force, well, or just let us call it P instead of F. Or let us call it F because I think they called it F. Okay, F and minus F. So F then is the force applied by the satellite on the shuttle. Actually, let me just flip the directions. That would be F and that would be minus F. So F would be then the force applied by space shuttle A on B. So that would be equal to the ejection force that A applies on B. And these are the only two forces acting on this system. So now notice, if I consider the combined system, okay, look, there could be thrust forces acting on the system, like the engines thrusting the space shuttle like this. Also, there could be thrust forces like this. But if I consider the combined system, and if I consider the sum of forces along the vertical, along EZ, so sum of forces along EZ is equal to 0. Of forces for combined system along EZ is equal to 0. Is equal to 0. So basically what this says is that the linear momentum of the system during collision or during ejection, during ejection is conserved. So the linear momentum of the system, which system? The combined system of A and B. Of the combined system of A and B is conserved during ejection. Okay, so then I can write that the linear momentum of the system pre-ejection is the linear momentum of the system prime post-ejection. And what is the linear momentum of the system? It's the sum of the linear momenta of the constituents. So that's MA VA plus MB VB is equal to MA VA prime plus MB VB prime. In particular, we're interested in the velocities along EZ, so I'm just going to project the whole equation along EZ. MA really though VA and VB are the same pre-impact, so maybe I'll just combine and I'll just say MA plus MB, and I'll say that VB dot EZ minus V8 dot EZ, I'm just gonna call that V dot EZ. Okay, so then instead of having two unknowns, and I'll remove the two unknowns, I'll just keep one unknown, V dot EZ, and I'll remove that one equation. Okay, so now I have three unknowns with one equation. I did some renaming here. Okay, three unknowns, one equation. Cool. MA dot NB V dot EZ is equal to MA VA prime dot EZ plus MB VB prime dot EZ. Okay, so this here, ladies and gentlemen, is our second equation. So we have one equation, two equations for three unknowns. Let us see if we can think of any more equations. Do we have any quantities given? Because I don't think we can find any more equations. The space shuttle launches an 800 kilogram satellite by ejecting it from the cargo bay. As shown, the ejection mechanism is activated in its contact with the satellite for 4 seconds to give it a velocity of 0.3 meters per second. In the z direction relative to the shuttle. Determine the component. Okay. So I think we have one too many unknowns here. But I think the answer is actually quite simple, that initially pre-ejection, the space shuttle and the satellite, they're not moving up and down along EZ. So then this would be equal to 0. So that gets rid of one unknown. If this is equal to 0, then I'm just left with these two equations. VB prime minus V dot EZ minus VA prime dot EZ is equal to 0.3, and then MA VA prime dot EZ plus MB VB prime dot EZ is equal to 0. So I can solve two equations, two unknowns, for VA prime dot EZ, that's just a scalar, and VB prime dot EZ, that's just a scalar. And I can report basically what the problem is asking for, which was VA prime dot EZ. Okay, cool, that's awesome. I think we're not done yet. There's still one more part of the problem. We need to find the time average of the ejection force. Okay, we need to find the time average of the ejection force, and we're given that the ejection is happening in a period of 4 seconds. The time average of the ejection force, which is this force F acting on the satellite. So then we're gonna need to consider the linear impulse linear momentum equation just applied to the satellite on its own. Because if we consider the whole system, F is the whole system of A and B combined, F is internal to that system, it cancels out. But if I consider the satellite on its own, then F is external to the system. So then, for the system of the satellite alone, for the system of A alone, I can write the integral of F dt is equal to for B alone, B, the integral of F applied on B dt is equal to GB prime minus GB. Okay? From basically integrating T pre-impact to T post ejection, not impact. And I just need to apply this along EZ, so I can just project. The forces along EZ applied on to this is just this force F here, its magnitude basically. So I'm going to call this F integral from, basically they said that the ejection is taking 4 seconds. So I have some time 0 and then some time 0 plus 4 seconds. Or time 0 is basically the just time pre-ejection. T pre-ejection and then T pre-ejection plus 4 seconds. And that's equal to MB VB prime dot EZ minus VB dot EZ. Okay, I want to find, remember these values I know already. VB is 0 and VB prime we solved for. So then I can find this integral, the integral of F dt from the time just before ejection and then the time 4 seconds later just after ejection. But really they're asking for the average force during ejection. So if I think about this magnitude F in time, I have T pre when ejection starts and T post, and during this interval If I plot F, it's varying in time, right? Maybe I'll draw a simpler curve, kind of. Ooh, F is varying in time. Now this integral, I'm gonna call it I for the linear impulse of the force F. This integral I, what is just equal to is the area between F and the curve. So this is my I, my integral I. Okay? Now what is the average force? The average force by definition is some value, right? It's some average value. What makes it an average value? It's an average value such that the area of this rectangle now on the same time interval is equal to I. So basically the I, which is the integral of f dt from t pre to t pre plus 4, that's equal to the time interval, which is basically 4 seconds, t post minus t pre, the time interval, which is 4 seconds, times the average force. So I can replace I by 4 times the average, and that should be equal to mb vb prime dot ez. Now mb vb prime dot ez I know, so I can just calculate f average is equal to mb vb prime dot ez over 4, and voila, that's it. That's the average ejection force.